Hi and welcome to Module 7, and we're looking at Inquiry Question 5, Reactions of Acids and Bases, or Organic Acids and Bases, and today we're looking at esters. Now esters is a new group that we haven't seen before, and we're going to just do a little bit of background information before we actually cover the syllabus outcome that's there on your screen, which is investigate the production in a school lab of some simple esters. So what is an ester? So have you ever walked into the bakery and smelt that lovely smell of bread, or into the coffee shop and that aroma of the coffee, or those nice banana lollies that happen to be a favourite of mine? That smell, the perfume of all of these favourite scents are due to our esters. So what we're going to be doing today is looking at that topic of esters and investigate a little bit more about what makes that smell so characteristic. So esters are in so many different products that we have, particularly in the perfume industry. We also have them as flavorings in our food industry, so they are a really, really important part of organic chemistry. And look, there's some things on our screen there, some organic solvents. So acetone in your nail polish remover, that nail polish remover smell is due to the formation of those esters, polymers in industry and so forth. So let's have a look at what our esters are. So they're another functional group that we're going to be looking at today, and they're characterized by the general formula RCOO R dash, where our R and our R dash are our hydrocarbon chains. So if we look at the group in the picture below, we can see that here we have a linkage point, that's COO. So if we're looking just in this point here, this is our linkage point where the two hydrocarbon chains R and R dash come and join. So our R comes from one group of organic compounds, and our other group, the R dash, comes from a different group. So let's look at that a little bit further. So the two things that actually react together to form these esters with their characteristic smell are an alcohol and a carboxylic acid. And when they do react together, they form esters in a process called esterification. And esterification is an example of a condensation reaction where we've got two reactants combining, and what we're actually getting is our ester, but we're getting the elimination of water. And when we do that, we're forming an alkyl alkanoate, another one for you to get your mouth around. So you can see here in our equation below, it's actually an equilibrium equation. So it's an equilibrium reaction. So in the case of the reverse reaction, it would undergo hydrolysis to the water is given there. So hydrolysis is taking it in that reverse reaction, and that water would then recombine with that alkyl alkanoate and form our alkanol and our alkanoic acid again. So how do we make this ester? Now it's going to obviously be a lot easier to understand this, the naming and the process, by when we actually come about making one in the lab, which we will do. But let's look at the theory first. To name this ester, we need to first of all locate that linkage. And again, as we said in the previous slide, here is our linkage group here, that COO. That's telling you that's where the two things are joining there. So when we are forming this, it helps to tell us what are the parent alcohol and what is the parent acid. Now the parent acid, carboxylic acid, is going to be characterized here by that double bond. So we know a carboxylic acid is our C double bonded to an O and then an OH group, characterized by that SCU. And we can see here that the OH part of that carboxylic acid has gone, and over here this oxygen belongs to the alcohol, but its hydrogen has gone. So the hydroxyl group from the carboxylic acid has combined with the oxygen from the ethanol, or the, in this case, ethanol group, and is forming the water. The rest of the compound then is linked together at that O and helps us form our group. So let's have a look at what we've got. We have got a 2-carbon chain here, our parent alcohol. So our parent alcohol will then be ethanol. And looking on the other side, we have a 2-carbon chain. It's really important that you don't forget to include that C in your naming. So in this one, we've got ethanoic acid as our parent acid. And when they join together, what's happening is we have our ethanol, and it's the substituent group in the product. So it will be characterized by an ethyl group. So it'll be an ethyl, and then instead of ethanoic acid, it's ethan, and the E is dropped, and O8 is placed in instead at the end as its tail and its suffix for the functional group of an ester. So it's an ethyl from the alcohol, ethanoate from the carboxylic acid. So let's have a look at another one. So here we have got ethanol reacting with butanoic acid. So what's going to be formed in this case? So again, our OH from our butanoic acid is going to combine with the hydrogen from the ethanol and produce our water. So what then happens is we have that linking occur over this H bond. This diagram's not really drawn in an easy way for you to see what's happening, but the bond here is linking. So this bond will join up over here with our C over this side. So we are going to get our parent chain. So our parent chain is going to come from our alcohol. So it is an ethyl group. And then we have got our butanoic acid. Our butanoic acid is going to then be forming a butanoate. We drop the E from the butanoic and add an O8 instead of an OIC. So we're going to get ethyl butanoate as our ester. And in this case, it's a really nice pineapple smell. So think pineapple lumps, another one of my favorite lollies. Let's look at another example. Here are 3 that I want you to have a go at below. So during esterification, what's happening is the making of an ester. Our OH is removed from the carboxyl group, the hydrogen removes from the alcohol, and they combine to form water. And the product that we also get is an alcohol alkanoate. So let's have a go with one of these, for example, butanoic acid plus ethanol. So what I want you to do is draw out the structural formula of butanoic acid, draw out the structural formula of ethanol, and have a go at doing the product. We'll come back and we'll see how you go. Okay, so firstly, did anyone pick up my mistake in the video? Over here, I forgot to have the double bond O in for the carboxylic acid, so hopefully you did pick up on that one. Back to our other question. The first one we've got there is the one we have just done, so it doesn't hurt if you went ahead and did that one anyway. But looking ahead at the second one, propanoic acid plus methanol, let's look at that one. So here we've got propanoic acid plus methanol. So if you draw your propanoic acid, you can see here again, I've got the carboxylic group with the double bond O and the OH there. And I've drawn my methanol with the OH on this end just over there, so it's a lot easier for us to see what's going on. So again, this H and the OH is being taken out, and that will be our water. So then what's happening is here's our linkage just here. And simply now that we've removed that water, we can just join those bonds up. So looking over here, you can see the 1, 2, 3 double bond. I didn't leave it out this time, the double bond to the oxygen, and here straight into the oxygen and the rest of the alcohol group. So in this case, we're getting methyl propanoate plus our water. How'd you go? Have a go at the next one, and we'll do a heap more practice, heaps of practice in class, and also do the prac, which hopefully will help consolidate some of that learning, the naming, and so forth. See you then.